My name is Alaina, and I'm here with Erik Centeno, Rafael Figueroa, Evan Shi, and Lycia Tran. Our PhD mentor is Cheng, and our faculty advisor is Professor Durgin. Our project is on next generation transparent rectifying antenna design for space solar power. With the increase in the energy requirements around the world, it is essential that we find alternatives for power generation. Space solar power has the potential to reduce the dependence on fossil fuel power plants that cause pollution and climate problems. So, how does it do that? We first need to talk about what space solar power, or SSP, is. Let's take a look at Figure 1, which illustrates one popular SSP system. It consists of a solar collection satellite in geostationary orbit that collects and transmits solar power to a ground station via a 5.8 GHz microwave signal. Covering this ground station would be a simple microwave frequency circuit with an antenna that rectifies this power to direct current, providing sustainable power to an energy grid. The key advantages of SSP are the ability to provide very consistent, renewable energy in a large scale. A geostationary orbit ensures that the satellite is always above the same point on Earth and allows for nearly constant energy generation even at night. Because of that, it has an advantage over other renewable technologies such as the wind and terrestrial solar that depend on weather for efficiency. The major drawbacks are the complex setup and the costs associated with both the collection satellite and the ground station infrastructure. Therefore, SSP is a promising alternative energy source that needs to display economic feasibility to the general public and policymakers. In order to do this, we aim to reduce the overall cost of the ground station. Now, Erik will tell us a little bit more on how we plan on doing this.
Thanks, Alaina. So as she just mentioned, our group is attempting to reduce the cost of an SSP ground station. A ground station is comprised of many circuits called rectennas. Our group is focusing on cost reduction efforts for these devices. Here is an image of the rectenna that our group manufactured last year. A rectenna is a circuit which takes in an AC source, in this case the 5.8 GHz signal, through an antenna. Our antenna is pictured here on the left and converts this AC signal to DC using the charge pump, or the right side of the circuit. The DC output, shown on the right, can be used to power a variety of loads, or be stored in batteries. In the middle of the circuit, a capacitor functions as a filter, and the diode package is used for the rectification of the AC signal to DC. Over the past several years, this team's main objective has been simple: to reduce the cost of an SSP ground station and increase commercial feasibility. We plan to continue to do this by first replacing the ground plane of our working prototype with a wire mesh to increase transparency. This would allow for multi-purpose use beneath these panels of rectennas. Additionally, we want to redesign our antenna to improve the gain and decrease loss to maximize the power transferred to the charge pump. Lastly, we are moving from glass to a less fragile acrylic substrate to make the prototype easier and safer to handle. In order to produce rectennas, we first start with the simulations of the antenna and charge pump. Our 2x1 patch antenna array is simulated in HFSS, High Frequency Simulation Software, shown here. The colorful bubble above the antenna is the gain pattern, a visual representation of the areas where power can be received or transmitted to. The red area shows the maximum gain of this antenna, around 7 dBi, which is an increase from last year's 3 dBi single patch antenna. This is an EagleCAD layout of the charge pump after it has been simulated in an advanced design system. The rectangles show matching stubs in the circuit, and the spacing shows where discrete components would be joined. You can see the spacing for the capacitor and the diodes here. We then send this layout to a laser cutter to create a stencil for our circuits. Lycia will cover this process in much more detail later on in the presentation. We have reiterated that the overall goal of our project is to reduce the cost of the ground station. This is a graph which shows the cost comparison between typically used optimized RF substrate, Rogers, and our clear acrylic substrate. Rogers is popular in the RF industry as it has been studied and characterized over a long period of time and is intended for use in these types of circuits. Commercially available acrylic is not specifically manufactured for use in RF circuits, but our research has shown that it is possible to design circuits geometrically to satisfy the RF parameters of this substrate. As you can see, the acrylic is nearly 2.8 times less expensive than the Rogers RF substrate. Rafael will now go into more detail on our results thus far while using this material.
Thanks, Erik. First, I'd like to talk about our antenna's performance at the target frequency of 5.8 GHz. The most convenient method of displaying our antenna's performance is with the use of S parameters. In particular, I will be using S11, also known as return loss. Simply put, the return loss is a measure of how well our antenna will accept electromagnetic energy of a particular frequency. Our return loss plot contains two traces. The red trace represents the simulated return loss generated by HFSS. This is the program we use to design the antenna. The blue trace represents the actual return loss data measured in the lab using a vector network analyzer, also known as a VNA. As you see, the simulated and measured return loss are fairly similar at 5.8 GHz and is measured to be about negative 11 dB. This is annotated on the graph by the black vertical dashed line. There was a notable deviation from expectations around 7.1 GHz. This appears to be a second resonant frequency, which warrants further investigation. Here, we display an image comparing our 2x1 microstrip patch rectenna using two different ground planes. Our first iteration towards a transparent rectenna was to use a semi-transparent ground plane. This is achieved by substituting the solid copper tape depicted on the left with a fine mesh conductor shown on the right. You may wonder how it is possible to have a functional rectenna with many holes in the ground plane. This is made possible by ensuring that the mesh is substantially smaller than the wavelength at the frequency of operation. Under this condition, the mesh will appear as a solid plane to the comparatively large electromagnetic wave. An initial test was conducted to validate this claim, yielding positive preliminary results. However, due to unforeseen circumstances, the team was unable to obtain a hard copy of the experimental results before losing access to the lab. Now, I'd like to introduce Evan to present our charge pump results.
Thanks, Rafael. Here we have the efficiency of the second part of the rectenna, the charge pump. This is the part of the circuit that converts RF power to DC power. So this is a simulation of that circuit that we made in Keysight ADS, and this measures how much DC power we'll get at the output for a given input RF power. We optimized this curve to be more efficient at higher power levels. The peak efficiency is around 47% at 5 dBm, but stays steady above 40% at power levels above 1 milliwatt, which is 0 dBm on the graph. The actual measured efficiency would be lower due to fabrication errors and non-idealities in the substrate, but we weren't able to do that before campus closed. Last year, we saw a decrease in efficiency of approximately 6 to 7% from the simulation, so we expect to see something similar with this prototype. Here we have a calculation for how much power a single rectenna would get if there was a 700 watt source 10 meters away, which is a test that we could have done on the roof of Van Leer. The inputs to this calculation are transmit power, distance, frequency of operation, transmit antenna gain, and receiving antenna gain, all of which are known quantities. About 2/3 of a watt of RF power enters the charge pump, and then after conversion to DC, we have approximately 1/3 of a watt of useful DC power. Now, this might seem absurdly bad. 700 watts turned into 1/3 of a watt is not very useful. However, the key thing to remember is that this is a single rectenna, which is a little bit larger than a credit card. For a real demonstration, you would create a large array of these devices, and the real ground station would have millions of rectennas. Lycia will now go over the fabrication method and future work.
Thanks, Evan. Keeping our goal of quick and cheap manufacturing in mind, our fabrication method was quick, simple, and inexpensive. First, we created a drawing of the rectenna on Eagle and used a laser cutter to cut out the rectenna on a spare piece of acrylic, thus creating a stencil we could use. We placed copper tape over a different piece of acrylic and then placed the stencil on top of the copper tape. We then used a sharp blade to cut out the rectenna design. Once the design had been cut out, we peeled off the excess copper foil, and this is what is being shown in the picture on the right. We then attached wire mesh to the other side of the acrylic using tape and formed the electrical connection between the ground plane and the rectenna. Finally, we joined the discrete components onto our rectenna using non-conductive adhesive strips. Our observations from our tests showed us that the efficiency and output power improved from last year due to increased antenna aperture in our new 2:1 patch array antenna. We also found that we had a return loss of negative 12 dB at 5.8 GHz while testing our solid ground plane rectenna. We also found that with the materials and fabrication techniques we used, we were able to manufacture our rectenna quickly and inexpensively. Finally, we found that the rectenna was still functional when we exchanged the solid copper ground plane for the mesh wire ground plane. Our future work includes collecting additional data for our meshed rectenna, gathering the same data we had found for our solid ground plane rectenna, and seeing how the two compare. We also want to optimize our antenna array size to deliver the maximum amount of power acceptable for our diode. We would also like to conduct a high-power magnetron test, so testing our rectennas with a high-power magnetron that outputs 700 watts of power at 5.8 GHz, and seeing how much power our rectenna receives. Finally, we want to see how the inconsistencies that occur when we cut out our rectennas affect our rectenna, and seeing how significant these effects are. Listed here are our resources that we used. Here is a list of all of our contact information. Feel free to email us with any questions you may have. Thank you for watching our video.